Investigating dy dx. To begin our discussion, we're going to look at what is called explicit differentiation. So far, all of the derivatives we have taken have been of functions in explicit form, meaning the dependent variable, usually y, of the function is isolated and written with respect to the independent variable, usually x. The functions below are written explicitly. So notice that in y equals 3x to the fourth plus 2x, y is isolated, it's by itself. That's why we call it explicit. In this here, we have a function f of t is equal to 1 over the quantity t minus 1 squared, and again, the f of t is isolated. And in our third one, we have w is equal to the square root of 6k, and again, this is written explicitly because one of the variables, in this case the dependent variable, is written, or it's isolated, it's by itself. Using various rules for differentiating, we know that the derivative of these functions are as follows. For y is equal to 3x to the fourth plus 2x, y prime will be equal to 12x cubed plus 2. If f of t is equal to 1 over the quantity t minus 1 squared, f prime of t will equal negative 2 divided by the quantity t minus 1 cubed. And if w is equal to the square root of 6k, w prime is equal to 3 over the square root of 6k. Again, the differentiation is straightforward. What is dy dx? There is one more notation we have used to label a derivative of the function, given by these three examples here. So far, only the terminology involved with this notation has been discussed, and that is the derivative with respect to the independent variable, whether it's x, t, or k. The meaning and value behind this notation has really not been taught as of yet, because it would have been very confusing when first learning differentiation rules, especially when we only worked with the functions in explicit form. Next, we're going to talk about greater detail of the notation dy dx. Continuing our discussion, what is dy dx? Now that we are more familiar with differentiation, we can investigate the notation dy dx a little further. Let's look at the first example from previous discussions. Y is equal to 3x to the fourth plus 2x has given us a derivative dy dx is equal to 12x cubed plus 2. First, we have to clear some assumptions that we have been making without knowing. Because the function is written explicitly, sometimes it is assumed what variable we are differentiating with respect to because it's obvious. In other words, because x is the variable in the function, the dependent variable, we differentiate with respect to x automatically. This assumption leads to a temporary misunderstanding that only the side with the independent variable, in this case x, is being differentiated. What perhaps you didn't know is that all this time you were differentiating both sides of the equation with respect to the independent variable. You might ask, what does this mean? We're going to break this down step by step. So when we say the phrase, find a derivative of y is equal to 3x to the fourth plus 2x, that is a simplified version of the full question being asked, which is, find a derivative of y is equal to 3x to the fourth plus 2x with respect to x. This last phrase right here has been assumed, and we have not really been mentioning it. So up until now, we've made the assumption that dy dx is simply the notation that identifies the derivative function. But here's what's really happening. The notation d over dx refers to taking the derivative with respect to x. That's an important note. You see d over dx, that's what's happening. It's taking the derivative with respect to x. So we preface each term of the function on both sides with the command d over dx. So what's really happening is d over dx of y. Then we take the derivative with respect to x of 3x to the fourth. d over dx of 3x to the fourth. Then we take the derivative with respect to x of 2x. Continuing with our discussion of what is dy dx. Now, When we take the derivative of each term, this is the part that has not been emphasized up until now. So the derivative with respect of x of y and the derivative with respect to x of 3x to the fourth plus the derivative with respect to x of 2 to the x will look like this. The derivative of y is 1. So when we have the derivative with respect to x of y, it turns into 1 times dy dx. So we have been using the notation dy dx all along. By writing dy dx next to the derivative of y, we are stating that the derivative of y has been taken with respect to x. Continuing on with our discussion about the notation dy dx, I'm going to pick up here. Previously, we discussed that the derivative of y is 1. So when we take the derivative of y with respect to x, we see that we end up with the notation dy dx. Now, with the derivative of 3x to the fourth becoming 12x cubed and the derivative of 2x becoming 2, what really happened was this. When we take the derivative of 3x to the fourth with respect to x, what we write down is 12x cubed. Then you take the variable x, so it's the derivative of x, with respect to x. dx over dx cancels out, and we're just left with the term 12x cubed. The same thing can be said with the derivative of 2x with respect to x. Okay? We take the derivative of 2x is 2, and then you identify what you're differentiating. You're differentiating the variable x with respect to x. Since it's dx over dx, they cancel out, and we're just left with 2. So, in summary, with the remaining terms, we are taking the derivative of x with respect to x. So the notation becomes dx over dx, which cancels out. That's why we never saw or noticed it before. As we continue our discussion, what is dy dx? Let's ask ourselves, why is this distinction so important? Well, to illustrate that, I'm going to offer the following example. What if the question we're asked, find the derivative of y is equal to 3x to the fourth plus 2x with respect to y? Now in this case, each term is differentiated with respect to y. So it would be set up like this. The derivative of y with respect to y is equal to the derivative of 3x to the fourth with respect to y plus the derivative of 2x, again with respect to y. Finding the actual derivatives, the derivative of y will be 1, and notice I put dy over dy, and note that they cancel out. The derivative of 3x to the fourth will be 12x cubed, and note dx dy, and the derivative of 2x will be 2, and again note that there's a 2x dy after that. So cleaning this up, we have 1 is equal to 12x cubed dx dy plus 2 dx dy. So notice that the numerator indicates the variable which is being differentiated, and the denominator indicates the instructions desired to differentiate with respect to, in this case, y. As we continue our discussion and exploration of what is dy dx, notice how the numerator is representing which variable we took the derivative of, and the denominator is representing the instructions desire to derive with respect to y. We're going to go a step further now. What if we were asked to find the derivative with respect to a different variable that's not even there, such as t? We're going to go back to our example. Y is equal to 3x to the fourth power plus 2x, and we want to find y prime of t. So what we do is we differentiate each term with respect to t. So we have the derivative of y, which will be 1, dy dt. Then we take the derivative of 3x to the fourth, which will be 12x cubed, this case dx dt. And then the derivative of 2x will be 2, and again I indicate dx dt. The numerator indicates which variable you're differentiating, and then the denominator indicates how to derive with respect to, in this case, t.